Okay, let's start. Welcome everyone to the first edition of the online seminar series on numerical linear algebra. So this is organized together with Melina Freitag, Stefan Güttel, Jörg Liesen, Valeria Simoncini, and Bart van der Eycken. So when all the conferences and workshops in our field, in particular the Householder Symposium, got cancelled, kind of discussed among different people in the field what would be a good way of compensating at least a bit this loss. And what we came up with quite quickly, which found wide acceptance, is to have a weekly seminar series. And then we started organizing this, and we are a bit overwhelmed by the success. So far we have 900 registrations from 70 different countries who are interested in following the seminar series. And so far on Zoom, we have already 290 participants and increasing. And so I hope this will be quite interesting for everyone. We have a great lineup of speakers so far. So the talks will be every Wednesday at 4 p.m. Central European time. You see the list of the next 5 speakers. And I believe those are some of the most influential and most visible persons in our field. And they are also representing different aspects of our field. And in particular, the first speaker, I'm very happy and proud that we have Nick Higham, who has agreed to give the first talk. We all have his books on our shelves, or maybe rather, if you didn't have the time to bring it from your university, it's on your laptop at least now. Or if you don't have the books, you should get them. They are great books. I learned a lot. It also prevents me from writing ever a book because I'm just humbled by the care and the dedication Nick put into these books. So he's a role model and is a great researcher in our field. I will not say much further. Before we start with his talk, he will talk about are numerical linear algebra algorithms accurate at extreme scale and low precision. Before we start with that, I would like to make one comment. So at least for this very first edition, we are not allowing questions during the talk, even if you joined via Zoom. So you have 2 ways of asking questions. If you joined via Zoom, you put a question in the Q&A, or you put a question in the chat of the YouTube channel. These questions are monitored and will be collected by Stefan Güttel for Zoom and Melina Freitag for the YouTube channel. And then we will synthesize them and we'll formulate them after the talk to Nick Higham. So stay in. So, and he will respond to these questions after the talk. Okay, without further ado, I would like to ask Nick to start his presentation. Thank you.
Okay. Okay, so hopefully you can now all see the screen. Well, first of all, I would like to thank Melina, Stefan, Daniel, Jörg, Valeria, and Bart for organizing this series, and also for the kind invitation to speak in it. And I should say, if you'd like to get hold of the slides, they're available from the URL shown on my first slide here, bit.ly ENLA1. So you're welcome to download the slides from there. So the fundamental question I want to ask in this talk is whether our numerical linear algebra algorithms are effective at very large dimensions and at low precisions. And for context, think about the forthcoming exascale machines, which are going to be solving extremely large problems, and the half precision arithmetic that's already available on many of today's GPUs. So this work is a collaboration with a number of people. I'd like to acknowledge them on this slide here. And let me talk about 2 trends in scientific computing. So first of all, problem sizes are certainly getting bigger. As I mentioned, we have exascale machines just around the corner. And also the unit roundoff, which is the measure I will be using as a measure of precision of the computations, is also getting larger thanks to the availability of low precisions. And the point is that our rounding error bounds typically are of the form some function of the dimension times the unit roundoff times other factors. So the fact that these two terms, f of n and u, are getting bigger really raises questions about whether I guess 70 years of experience in digital computing and of understanding rounding errors, whether that experience is still providing useful information. So let me say a little bit more about the dimensions and the roundoffs that we have nowadays in practice. So I'm going to think about dense linear systems to start with. And so the question is, how big are the systems that we're solving? And I think a good way to answer this is to look at the top 500 list. So this is the list of the world's fastest computers as measured by the time it takes them to solve a random dense linear system. Now, by their very nature, these machines run fastest when solving very large problems. So these will be pretty much the largest problems they can solve that are used to enter the top 500 list. The top machine at the moment, and it has been for the last 2 years, is Summit at Oak Ridge National Laboratory, which has, as you can see, a large number of CPUs, a large number of GPUs, and the entry that Summit put in to achieve this #1 position, and you can find this on the top 500 website, had a problem size of 1.65 times 10 to the 7. So that's the current large sizes, or maybe largest, that are being solved. And we can expect n to be 10 to the 8 or more once we get to exascale machines in a year or two. What about the floating point arithmetics? Well, here is a range of widely used precisions in scientific computing. FP64 and FP32 are the IEEE double and single precisions that we're all most used to. FP128 I've put there, that's also an IEEE arithmetic, although only available in software. That's quadruple precision. But I'm particularly interested in the green lines in this table. So FP16 is the IEEE half precision format. bfloat16 is the format introduced by Google, and it's being adopted by ARM and Intel, amongst others. So these are pretty low precision. If you think about FP64 as corresponding, roughly speaking, to about 16 decimal digits worth of precision, FP16 has 4 digits, bfloat16 has only 3 digits. So these really are pretty low precisions. But they are now available in hardware and being widely used. And in particular, the motivation for these low precisions nowadays is largely from machine learning and deep learning. And I've included a couple of quotes here to give a feel for this. So what's now a relatively old paper by Corbariu, Benji, and David in 2015, they were already finding then that low precision was enough to train networks and then to run the trained networks. I also include a quote here from a recent paper by Dean, who's at Google, who points out that deep learning models are very tolerant of reduced precision computations. Now, I see on Google regularly patent applications or patents that have been granted for hardware implementations of low precision. Here's just one I've shown on this slide here from about a year ago, an Intel patent for 16-bit floating point vector dot products. So there really is a lot of interest in low precision floating point arithmetic now, motivated particularly by deep learning. Now, let's look at the simple operation and understand its rounding error analysis. So this is the inner product of two vectors. X and Y are both vectors with n elements. And the standard Wilkinson style bound is shown here. So the relative error, or the absolute error, the computed inner product minus the true inner product, is bounded by the problem size times the unit roundoff times. Now, mod of a vector means you take the elements, take the absolute value element-wise. So mod x transpose mod y plus second order terms. So this is the bound that Wilkinson states in one of his early papers, and it's still about the best bound we have today. So it's a worst case bound, so it guarantees the error will not be any larger than that, and it's approximately attainable. So you can find x and y for which that is an approximate equality. Okay, and we have a factor nu in the bound there. So let's focus our attention on n times u, and the question is, how big is that? We want it much less than 1. If it ever gets to 1, then our bounds are telling us essentially nothing. So really all the interest is in how big is that? How big is nu? Well, let's look at linear systems. So here I've quoted again Wilkinson standard result for linear systems, which I'm sure, like myself, many of you teach to your students. And so what we normally say is that the computed solution to x equals b from LU factorization has a backward error delta A. Then there's this bound that involves the norm of A, the unit round off, the growth factor rho n, and there's a term Pn that we say is some modest degree polynomial. And we normally say, well, let's just ignore the Pn and let's focus on the growth factor and see how big that can be. But can we really ignore the Pn term? Well, I think at best Pn will be n squared after taking norms. And let's look at what you have to do to enter the top 500. You have to solve a linear system, and you have to check that the relative residual is bounded by 16 NU. So this is the tolerance that's used. The left-hand side here is actually the backward error. So this is a backward error test to check that the system has actually been solved to a good backward error. Now we know that on Summit, n star was the actual n that was used was of order 10 to the 7, and we know that Pn will be about n squared at best. So if you work out Pnu, it's 0.03, which is about six orders of magnitude larger than it would need to be to pass this test. So the existing backward error analysis is certainly not telling us that we can successfully solve a system this large at this dimension. So clearly our error bounds are very pessimistic once we get to this size. In terms of low precisions, if we look at FP16, the IEEE half precision, and bfloat 16, the Google format, then you can see that for really very modest n, we're already hitting n times u equals 1. And yet, we know that deep learning is being successfully used at these low precisions. Yet our inner product error bound is order 1 here already for these relatively small n. So this is clearly a concern. Now, when I look at papers on deep learning that use low precisions, I don't usually find any analysis of the errors, of the rounding errors. And I would like to be able to say, well, we just can use our many years of experience and plug these numbers into our error bounds. But the fact is that the error bounds will not be very useful at these precisions. So what's going on, and are things really as bad as they seem? Well, I'll argue in the rest of the talk that things are better than they might appear for 2 reasons, really. The first one is that we don't actually compute inner products in the way I've shown or the way I've implied, and that itself leads to a lot of pessimism in the error bounds. And the second reason is that because we're used to thinking about worst case bounds, then clearly on average, worst case bounds can be very pessimistic. And I'll explain how by introducing some probabilistic ideas, we can get much more insightful and certainly much smaller rounding error bounds. So let's go back to inner products. So here is on the left, Sn, the inner product of x and y. And so the obvious way to compute it, you do x1, y1 plus x2, y2 plus and so on. And that's the error bound I showed you earlier. But that's not the only way we can compute the inner product. We can also break it into 2 pieces. So here I'm assuming n is even, and I'm computing in S1 the inner product of the first q entries. Q is n over 2. And then S2, I accumulate the inner product of the last n over 2 entries. And then I add them together. Sn is S1 plus S2. And if you do the error analysis, you find that the error bound now contains n over 2 rather than n. Why is that? Well, it's not too hard to see, because if you look at the original computation, we first of all form x1, y1, which has a rounding error. Then we add to that x2, y2. Then we add x3, y3, all the way up to x and yn. So x1 and y1 are hit by n different rounding error terms, and that's why basically we get the factor n in the bound. In the blocked form, x1, y1 are only hit by q rounding errors, and then 1 final rounding error when we add s1 to s2. So q is n over 2, and hence the overall constant is n over 2. Now, of course, we don't only have to consider breaking into 2 pieces, we can break the inner product into k pieces, which is what I've done here. So I'm assuming n is k times q, and so we have these q partial inner products of length k. We compute them, and then we add them together, and the overall error bound turns out to have a constant n over k plus k. The obvious thing to think about here is choosing the optimal k, and it's easy to see that it's root n. So in this case, the error bound now has a root n rather than an n in the as the constant, or 2 root n. However, I think k's root n is not necessarily a very practical choice. We have to keep in mind the idea of having a very good performance, but nevertheless, the idea of blocking clearly is going to give us, or is potentially going to give us a significant reduction in the error bound. And of course, none of this is really new. If we think back to LA-PAC, which is now nearly 30 years old, LA-PAC introduced the idea of partitioned or blocked matrix factorizations. And the block size, I think, chosen typically is something like 128, 256. And so LA-PAC is working on blocks. And for the same sorts of reasons that we get a reduction in the inner product, we get a reductions in the error bounds for all the standard computations like LU factorization, QR, and so on. So all the error bounds basically get a reduction in constant by a factor B. But this is not something that's that well known. If you look in the LA-PAC manual, for example, it states the error bounds in terms of PN. It doesn't mention the block size there. Standard textbooks they may mention block algorithms, but they don't mention really the block size in the error bounds. What did I say in my book? Well, when I talked about inner products, I did mention the idea of blocking the inner product. And I do have a comment early in the book that this improved constant will propagate into all the later error bounds, but that's really all I said. I didn't make a big thing of it at all. And I think the reason for all this is that, 20 years ago, n wasn't as big, we didn't have low precisions, and so we really weren't worrying so much as we might do today about these issues. So blocking helps, but we can actually do better. So I want to describe a new idea which is described in the context of summation, but clearly the same idea applies to inner products. So let's go back to just the simple recursive summation of n numbers. And I've shown you the little algorithm there that I'm thinking of. That's what I mean by recursive summation. So it's quite common to do this in a block form. And so the idea, rather similarly to what I just described for inner products, is you break the sum into pieces of size b. You add those pieces by recursive summation. The number of additions involved in that will be n minus n over b. Then you sum the partial sums. So there's n over b partial sums. And again, you would sum those by recursive summation. So this is a standard technique. Notice that most of the work, since b is a constant, most of the work is in step 1, because n over b will be much less than n. So we've got recursive summation here, recursive summation here. So the idea I want to investigate is, how about using a more accurate method at step 2? Because step 2 is of less cost than step 1, we can afford to do something more expensive. And if it's more accurate, it could give us potentially a benefit in terms of the overall error. So this is something I'm going to call FabSum. So the input to this algorithm, as well as the vector and the block size, is 2 other algorithms. You can have any fast summation algorithm and any accurate summation algorithm. So you do the individual blocks are summed with fast sum, and then these partial sums are finally collated by using accurate sum. So once again, accurate sum is doing quite a lot less work than fast sum, so we should be able to employ more accurate summation for accurate sum without affecting too much the overall performance. So what actually transpires when you look at the error analysis? Well, let's assume that these 2 summation methods, fast and accurate sum, both have backward error results of the form shown. So backward error is mu if bounded by epsilon fn and mu ia bounded by epsilon an. And it's not too hard to show that with FabSum, the overall backward errors, this term mu I, is bounded by, I've got the sum of the 2 individual errors and then the product of them. So the errors in fast sum and accurate sum actually combine additively in the first order term and then the second order term multiplicatively. So what does that mean in practice? Well, let's look at an example. Let's take fast sum to be recursive summation. And for accurate sum, I'm going to take something called compensated summation. I could also take recursive summation in extra precision. Now, compensated summation goes back to the 1960s with Gahan and Muller. And I won't write it down, but it's essentially like recursive summation, but with a few tricks inside it that try to estimate the error and then add the error back in as the competition goes along. So it's much more accurate than recursive, but it's also quite a bit more expensive. So for these two choices, I find that my overall backward error bound is b plus 1u. So the constant that was originally n for recursive summation is now b, which is a constant. So that's great. I've got down to a constant first order term. And I'm showing you the second order term really just to indicate there's nothing nasty hidden there. There is, of course, an n in there, and eventually this second order term will start to make its presence felt. But that will be quite a while before it does so. So the original error bound for recursive was nu. For block summation, n over bu. And now we've got that down to a first order term of bu. So a significant reduction by this idea of this sort of two-level computation. So does this work in practice? Well, here's an experiment in single precision. The data is a vector of elements drawn uniformly from the interval 0, 1. The block size is 128, and n goes from 10 to the 3 to 10 to the 8 here. So what I'm showing you are the errors for three methods. So blocked means blocked recursive summation with block size 128. So its error is increasing. Compensated summation has a fairly constant error, which is a very good error down here. And the fab sum, again with the same block size, 128, is doing about as well as compensated summation, which is significantly better than the blocked summation. Let's also try going on the interval minus 1 to 1. Again, random uniform numbers. So it's a similar situation. This time, the errors for compensated and fab sum are decreasing, and fab sum is a little bit larger than compensated, but still significantly less than the blocked summation. So we really do get a benefit from this approach, and we also have found experimentally that the overhead is extremely low. It's just a few percent overheads in doing this. Just one aside, you might ask, why are the errors decreasing on this slide and constant or increasing on this slide? And it turns out it's due to the mean of the data. So Theo, Mary, and I have some results that say if the mean of the data is 0, which is not the case on this slide, but is the case on this slide, that the factor n that you might get in the error bound disappears. So that explains that behavior. So what I've been saying so far is quite generic. Let me now focus on something that's much more hardware specific and specific to low precisions, block fused multiply add, or FMA. So what this is a hardware unit that carries out a small matrix multiplication and matrix addition. So we have A and B. A is B1 by B, B is B by B2, and we add that to C. So we have a hardware unit that can do this operation, A times B plus C, and return the result in D. So let's think of, we have two precisions, the U low, which you can think of as half precision, U high you can think of as single precision. So we're taking in two low precision matrices A and B, we're multiplying them, and the key thing is the operations here, the multiplication and the addition, are done at the higher precision in hardware by the hardware unit. And what we can do is we can take the output D and put it back in here as the C on the next operation. So we can have a sequence of these operations where where the output D is fed back in as the next C. And in this way, although the individual multipliers here are quite small, we can build up a general n by n, or indeed rectangular matrix multiplication. So what are some examples of such hardware? Well, there's the Google tensor processing units deal with square multiplication of size 256 or 128 using bfloat 16. NVIDIA, I'll say more about this in a moment, but they have a 4x4 matrix size. There was going to be an Intel neural network processing chip, although I think the project's been cancelled, but that was planned to have a matrix size of 32. And the recently announced ARM V8A has actually a rectangular multiply, 2x4 times 4x2 in bfloat 16. And the reason for the interest in these chips is that they're very fast, so they'll produce one result per cycle once they've got going. I should say that in the case of all this hardware, the exact details of what's going on inside these hardware units is usually not given by the manufacturers. And we found from our investigations with NVIDIA Volta that this is not necessarily fully IEEE compliant. So just to give an example, here's the NVIDIA situation. It's dealing with 4x4 matrix multiply and addition with half precision and single precision. So A and B are half precision, and C can be half or single, and the output can be half or single. The previous generation of NVIDIA chips, the P100, gave a factor 2 speed up in going from single precision to half, but with these tensor cores, that has now become a factor 8. So an 8 times speed up going from single precision to half precision. And you can see why people are interested in using this, not just for deep learning, but also for general purpose scientific computing. So the question is, what can we say about the error analysis if we do things this way? So let me analyze an algorithm for n by n matrix multiplication that makes use of a block FMA. And of course, this is an inherently multi-precision computation. So the overall error bound that we have derived, and this is stated component-wise, has a constant, and we want to know what this constant is. The constant f depends on the dimension n, on the block size b, and on the low and the high precisions. And I've given in this table just 3 very special cases. So the first thing we might think of for comparison is, what if you do the whole thing in low precision? So you'd basically have an error bound n times u low. Or you could do the whole thing in high precision. You'd have an error bound n times u high. But using the block FMA, where you provide low precision A and B, and internally it computes to the higher precision, the error bound, the first order part of the error bound is 2u low plus nu high. So what's happened in going from the first line to the second, the n has moved from the u low to the u high. And so if you think of u low as 10 to the minus 4, u high as 10 to the minus 8, that's a big improvement. That n term is now attenuated by a much smaller unit roundoff, as it would be if we worked entirely at a higher precision. So we're getting a significant benefit. And we still have the u low term here, the 2u low, but eventually the nu high will become of the same order as 2u low. And then we're doing very similarly to as if we worked entirely in single. So this is a very nice result. And this can be taken further to get similar results for LU factorization and for the solution of linear systems using the LU factors with similar sorts of statements about the error constants. So let me just show you one example on the NVIDIA V100. So the matrix dimension is on the x-axis. It goes up to just over 10 to the 7. The y-axis is the component-wise error shown here. Elements uniform on the interval 0 to 10 to the minus 3. This is to make sure we don't get any overflow. If you do the whole thing in single precision, you get the line at the bottom, this blue line. If you do the whole thing in half precision, you get the black line. But with the aid of the tensor core unit, so the TC32 means using the NVIDIA tensor core at its highest precisions, with single inside and single for output, then we're clearly doing a lot better than if we were working only in half, not as well as single, but the point is that the red line is obtained a factor 7 times faster than the blue line. So we're getting a factor 7 speed up and still doing significantly better than if the whole thing were done at half precision. So this mixed precision FMU is giving benefits in both speed and accuracy. There's one other thing that we have as an advantage here as to why our errors are often smaller than we might think. And it's because Intel chips have 80-bit registers. They have 80-bit floating point registers, which are probably being used by the compiler without us really knowing it. It's hard to know exactly when these are used. But our 64-bit double precision numbers, in many cases, the accumulations of things like inner products and sums are at least partially happening in these wider registers, and that will give us automatically more accurate answers much of the time. Okay, so that was some ideas on why we do better than we might think in terms of the way algorithms are implemented. But let's just return to the error bounds themselves. And I want to give a very nice quote from Pete Stewart. So Pete said in 1990, in the context of looking at worst case error bounds, to be realistic, we must prune away the unlikely. What's left is necessarily a probabilistic statement. So what Pete's saying is, if you want to get a bound that's significantly better than a worst case bound, you're going to have to really go for something that's probabilistic, where you're pruning away the very unlikely cases. Now, there is a rule of thumb that's quite well known, and Wilkinson has mentioned it several times in his writings. The idea is that you argue because of the statistical distribution of rounding errors, the function of n we get in our bounds can be replaced by its square root and still have a reasonable, a bound or an estimate. So this is a rule of thumb that a lot of people know about. There's no proof of that rule of thumb. The thinking behind it, I think, is essentially the central limit theorem. So the argument would be something like, let's assume the rounding errors are independent random variables and mean zero. Then if n is sufficiently large so that you can apply the central limit theorem, then you can get an estimate of the first order part of the error that would involve this square root. But it's impossible to quantify how large n has to be sufficiently large here. And you have got these assumptions on independence of the random variables. So I'd like to have something more precise than that rule of thumb. So let me go back to the tool that we use a lot in error analysis. This is what I use in my book, and everything's pretty much based on this. So the delta i's in this result are rounding errors bounded by the unit round off u. And what we often end up with is a product of terms 1 plus delta I. And we want to see how close that is to 1. So we want to bound the theta n in this equation here. So this result says theta n is bounded by nu over 1 minus nu, and I usually call that gamma sub n, but it's basically nu plus higher order terms. And so what I like to do is get a probabilistic version of this result, ideally with the n replaced by a square root of n under some assumptions. So I will focus in the rest of the talk on backward error results. So I'm going to have to make some assumptions on my rounding errors. So the first assumption here is just the usual model of rounding errors that says when you do any of the 4 elementary floating point operations, that you get a relative error delta bounded by the unit round off in modulus. The more interesting assumption, the second one, says that we're going to assume that you have a sequence of rounding errors, delta 1, delta 2, and so on, that are random variables of mean 0 and satisfy this condition here. So E here is the expectation operator, and the bar denotes a conditional expectation. So this says that the expectation of delta k plus 1 given delta 1 to delta k is the expectation of delta k plus 1. And that's 0 because we're assuming these rounding errors have mean 0. So this is called mean independence. The rounding errors are assumed to be mean independent, mean 0 random variables. They don't all have to be from the same distribution. And this assumption is certainly weaker than assuming that the delta I are actually independent. This is a weaker assumption on the rounding errors. So here's what we're able to come up with in terms of a probabilistic variant of the result I just showed you. So under the model I've just described, I called it model M, then we can bound the departure of this product from 1 by not gamma n, but gamma tilde n. And gamma tilde is basically lambda root nu plus second order terms. What's lambda? Well, lambda is a constant you could choose. And lambda then determines the probability that this result holds. Now, if you take lambda as 4 or 5, then this probability here is very, very close to 1. So in that case, with just a small constant lambda, you have a result that holds with extremely high probability. And the point is it now has the root n rather than the n. And Theo Mary and I had a weaker version of this result last year, but that assumed independence rather than mean independence. So what can you then do with this result? Well, one thing we can do is plug it back into our inner products and get a probabilistic variant of the result I started with. So the inner product x transpose y, I put the backward error on x. I could have put it on y equally well. So component-wise, delta x is bounded by this new constant gamma tilde lambda times mod x, which is basically lambda root nu, with a probability that will be close to 1 if lambda is not too small. So this is a probabilistic version of the result, the Wilkinson's that I showed at the start. Okay, and then we can, so once we have a result for inner products, of course, we could then get results for matrix vector products, matrix products, triangular solves, and LU factorization. And when you put all that together, you get this result shown here. Under the model, the computed solution to our system from LU factorization has a backward error. It's exactly the same form of bound as we have for the usual worst case analysis, but the gamma n has been replaced by gamma n tilde, and we now have a probability here. But once again, lambda doesn't have to be too big for this probability to be close to 1, and so we are essentially getting the root n behavior in the error bound. How does this fare in practice? Well, let's just try some examples. We've taken some matrices from Tim Davis's sweet sparse collection, varying matrices of size up to about 10 to the 4. We've solved X equals B with a random right-hand side. We've plotted the backward error. The blue line here is the worst case error bound. The red line is the probabilistic error bound with lambda as 1, and the yellow squares are the actual backward errors. And you can see the actual backward errors are all less than the probabilistic bound, which is much less than and growing more slowly than, because this is root n here rather than n growth. So the probabilistic bound is giving a much better idea of the behavior on these matrices from sweet sparse. So I talked about this mean independence result. Let me now finish off with an example where this really comes into play as being extremely useful. Something called stochastic rounding. Now, this is quite an old idea. It goes back to at least George Forsyth and Tom Hull in the 50s and 60s. But it's coming back into prominence again because it's being used in deep learning. So how does it work? Well, the idea here is I'm showing you two consecutive floating point numbers A and B and a number X that we want to round. So normally with round to nearest, we would round X to B because X is closer to B than to A. With stochastic rounding, you would argue as follows. You'd say, well, X is about 0.6 of the way along this interval. So I'll round to B with probability 0.6 and to A with probability 0.4. So you always allow rounding in either direction, but you bias the rounding towards the nearer of the 2 points. And the precise formulation is shown down here. These are the probabilities that we use. Now, this at first sight seems a rather crazy thing to do because clearly the actual error I'm incurring is at least as big with stochastic rounding as with round to nearest, because I'll either do the same as round to nearest or I'll go further to get my floating point number. And indeed, in the standard model, you have to replace u by 2u now for stochastic rounding. So why would we want to do stochastic rounding given that it has a worst case? Well, it's really precisely because it is probabilistic. So let me first of all, before I explain that, just state a result about rounding errors from stochastic rounding. So it turns out the rounding errors from stochastic rounding, well, they clearly are random variables by construction. You can show they have mean 0, and you can show they're mean independent. So they have this mean independence property we saw earlier in the model M assumption. That means I can now plug directly into the result I had a couple of slides back, where I had the tool that we use for rounding error analysis. And the assumption that the rounding errors satisfy model M is now automatically true. So what this means is that the rule of thumb that Wilkinson and others have stated is actually a rule for stochastic rounding. We can always replace NU by root NU in a worst case rounding error bound to get a probabilistic bound when we're doing stochastic rounding because of these properties up here of stochastic rounding. Let me give you a couple of examples to illustrate the benefits of this. So this is for an inner product X transpose Y, where it's a rather special case where every element of X is the same and every element of Y is the same, and these two constants are just chosen randomly. So what you can see here is n on the x-axis. The black line is the usual worst case error bound. The dotted line is the probabilistic error bound, and these blue circles are the errors from round to nearest when I compute the inner product with in the standard fashion. And you can see that the rounding errors from round to nearest are growing faster than root n. But those from stochastic rounding are growing slower than root n. So in this example, stochastic rounding is giving a much smaller error than round to nearest. Here's another example where X and Y have elements drawn from the uniform 0-1 distribution. Again, here's the worst case bound. The dotted line, that's the NU bound. This is the root NU, the dotted line. So round to nearest starts off well, but then the errors grow and grow. They cross the root NU line and start tending to 1. Meanwhile, stochastic rounding is happily producing errors that satisfy the root n bound, as we know they must do. So what's going on in these examples? Well, the point is the rounding errors from round to nearest are certainly not mean 0 in these examples. In the first example, it turns out that the errors are constant when the partial sums are between powers of 2 because of the nature of these constant vectors. In the second example, what's happening is that we have elements x and y from 0, 1. We have a large number of terms, and eventually these xi times yi's do not change the computed sum. So with round to nearest, they just disappear. However, stochastic rounding always has the chance of rounding up even when you're far from that floating point number. And that is enough to avoid this phenomenon that we call stagnation. So stagnation is when you have a sum of numbers and small numbers in the sum are unable to contribute to the sum in floating point, even though they can do if you were to work in exact arithmetic. So stagnation is what we saw in the second example. Stagnation starts to happen around about here with round to nearest. And beyond that point, all the xi's, yi's are not changing the sum at all at that point. So from what I've just shown you, I can conclude that stochastic rounding is immune to stagnation because we just argued that it always satisfies the root NU bound. In fact, you can even show that the expected value of the computed result is the true computed result with stochastic rounding. And so I think this explains the success in deep learning of stochastic rounding, because in deep learning, they're working in low precision, they have large inner products with many small terms, and for those small terms to have a chance of contributing to the sum, stochastic rounding gives them a chance of doing that, whereas round to nearest would always just round them back and the sum would not increase. So stochastic rounding is of interest, at the very least, for this property of avoiding stagnation. So let me finish off with some conclusions then. So I think numerical algebra is much more accurate than our worst case error bounds would suggest. And the reasons are summarized here. So block algorithms that we've had for many years give us a constant reduction factor by the block size. If you want to use FABSUM, this new idea for summation, that gives even bigger reductions. The first order terms now down to a constant, depending on the block size. When working in low precision with hardware, such as the tensor cores and tensor units from Google, these block FMAs are very useful. They also give a reduction in the error from what you would expect given the base low precision arithmetic. They can basically reduce factors n down to 2. We have this automatic benefit from the 8-bit registers on Intel chips. And the actual rounding error bounds can be improved if you're willing to work with probabilities. So under this assumption of mean zero, mean independent rounding errors, you can replace NU by root NU. And importantly, stochastic rounding does satisfy these assumptions. So it always has this root NU behavior. So stochastic rounding always satisfies the rule of thumb that we've had for many years. And just finally, if you'd like to know more, there's a list of works where you can find all the details of what I've been saying today. So I will finish there.
Thank you very much, Nick. It was a very clear talk, so we have only a small number of questions. Let me start by 2 questions posed by Thibaut Simic and Roman, which relate to slide 18 and 19. Mm-hmm. These are some of the numerical experiments. The first question is there some kind of explanation why the FAB algorithm attains a lower value for small n? Sorry, a higher error for small n than the other 2 methods?
A higher error for small n. Yes, that's right. So at the left-hand endpoint here, it's starting off a bit higher. I think it's because it hardly gets going, because remember the block size is 128. The problem size is 1,000. So the block size is quite large relative to n. So you need to have a much bigger n for the blocking to have any benefit.
Mm-hmm. And the other question relating to slide 18 and 19 was how were these results obtained? Like what programming language has been used?
These were done in MATLAB and using. So how do you get? Well, that was single precision. Actually, it was all single, wasn't it? So we have also done experiments in a half precision, and there we used a function chop that Sri Pranish and myself have written to simulate half precision in MATLAB. So we typically do our experiments in MATLAB if we can, but we have also got experiments at large scale in these papers done on suitable large scale hardware. That's particularly for the performance testing.
Okay. Any comments on how stochastic rounding is implemented in hardware? That's a question by Jans-Peter Zemke.
Yeah, that's an extremely good question, which I, of course, didn't say anything about. So my colleague, Matrices here, is a bit of an expert on this. He's done his PhD in our computer science department using stochastic rounding on the Spinnaker machine. So if you look at Mantas Matrices, he has a recent paper with Max Fassi on precisely this issue of how to do stochastic rounding. So I think there's a lot more work to be done there, because clearly, if you want to do it exactly as per the prescription, then this clearly sounds fairly expensive to do, because you're going to need to generate a random number. There's the question of what precision you do this at as well. So if you're building your own hardware, like our colleagues at the Spinnaker project were doing, they can do clever things in hardware that help them with this. But if you're using existing hardware, then there are some interesting questions on how to do it.
Okay, Daniel Kressner has asked how tight the bounds on the failure probabilities are.
They're still rather weak, because you can see here that here we take a lambda equals 1, and we still have errors well below the bounds. So these bounds are still weak. So there are, the errors are still smaller than what the probabilistic bounds would suggest.
Cleve Moeller asks how these results can be applied to nonlinear algorithms, for example, for solving eigenvalues, numerical ODEs, and so on.
A very good question, and I hope people will go away and work on that.
The last question from the Zoom chat that I'm going to post here is, how is success actually measured in deep learning applications? And possibly a related question is also, is it possible that when training machine learning models that somehow rounding errors are in fact built into the model? That's partly a question by Catherine Lund.
Well, again, a very pertinent question. I probably shouldn't speculate, because I read papers on machine learning. Their measure of success is usually specific to their application. I think there is some regularizing effect from rounding errors. That certainly may help, but I don't really want to speculate too much on those issues, because I think they're still very unclear.
Okay, thank you. I'm handing over to Melina, who has a few YouTube questions, I think.
Yeah, I've only got one question, apart from a lot of greetings from a lot of people around the world. And that one question is quite technical, from Thomas Mach. Do you have a physical Google TPU, so tensor processing unit, available for your experiments, or do you only have access to a Google Cloud TPU service?
We haven't used the Google tensor processing units. We have used the NVIDIA, and there's this recent paper here where we've been doing some detailed analysis of the NVIDIA V100. No, I haven't used the Google one. Okay, so that was the only question on YouTube. If you want to ask some more, Stefan, are there any more on the Zoom?
Yes, there's another one by Rebecca. Is there a connection between stochastic rounding and Metropolis-Hastings algorithm? i.e., is stochastic rounding converging to some stationary distribution with mean X transpose Y, for example?
Well, there's this result here that for the inner product, the mean of the computer result is the true result. What I can say is that stochastic rounding is related to other things that have been proposed in the past. There's something called Monte Carlo arithmetic that was proposed about 20 years ago. There's other forms of stochastic rounding as well, in addition to the one I've described here. So there's quite a variety of different ideas that lead to randomness in the rounding. But this is the particular one that seems to be of interest, or most interest right now today.
And the last question from Zoom is from Marcin. Can this be applied to Strassen-type algorithms for making them more stable? Or could this have any influence on these algorithms for practical implementation?
Yes, I think so. I haven't done it, but I think you could improve the constants in Strassen by using these results as well, because all you need is this basic lemma or basic theorem here, and Strassen itself will have these sorts of products appearing there. So I think yes. Indeed, Strassen is done in a block fashion anyway, so it will make use of this result if you want to make those assumptions required for Model M. Yeah.
Okay. Thanks, Nick, for the answers, and thanks for everyone who posted questions. I'm handing over to Daniel.
So I'll stop my share now. Okay, there we are.
Visible?
Not visible, but audible.
Okay, very good. Oh, now I'm visible.
No, both, yeah.
Okay. Thanks a lot, Nick, for your great talk. It was very instructive, very insightful. Thanks everyone for attending. So we are going to have this next talk next Wednesday, same time, 4 o'clock Central European time. It will be by Michele Benzi from Pisa on non-local dynamics on networks via fractional graph Laplacians. Okay, then I wish you all a good day and see you next week.
Thank you.
See you all. Bye-bye.